Okay. Before the break, where we finish off is we have two issues regarding the analysis. Okay, what are the two analyses that I'm going to highlight? The first is the location of the maximum bending moment and the maximum shear force are not necessarily on the same position. That's our first dilemma. The second one is the stress that we're going to calculate, okay, is going to be in the intersection between the flange and the web. Okay, so that is the area of interest. So what does that actually means? If we're going to place our element of analysis, okay, as you can see, the question did not say where is that element. Okay, we're going to position the element of analysis. The element will be exactly down here. Okay, the element will be exactly down here at the intersection between the flange and the web. Okay, it is at that region where failure will occur. Okay. So now we are going to do shear force and bending moment equations and diagrams. I know some of you have done 2P last term. You are very fresh, but I know some of you have done 2P probably a year and a half ago. You're not so sure. I will revise everything regarding shear force and bending moment equations. Okay, and this is required in our next two topics, which is on deflection. Okay, on deflection, you need to form the shear force and bending moment equation. And I believe you guys have done this before, even in math. Okay, when you take your math, probably there's an example on shear force and bending moment equations. Okay, so the first thing we're going to do is we're going to determine. Hey, come on, determine, you put here, determine the reactions at point B and point D. Okay. We are going to determine the direction point B and point D, and I'm going to copy the diagram over here, so I don't need to jump about, and you get a headache. I get confused. So this is and I'm constructing our free body diagram. X, Y, rotation about Z, and we know that this is our point B. We have a BY, and point D, we have a DY, and then over here is our point C, and over here we have our equivalent load, which is equal to 50 times 10 to the power 3 plus multiplied by 2.4 plus by 0.8. So this is equal to, pardon me, forgot my calculator. So 2.4 plus 0.8 is 160 times 10 to the power 3. That is our equivalent load because it's evenly distributed. And sort out the distance during this time frame. So from here to here is equal to 2.4 plus 0.8 divided by 2, 1.6. And then the distance from here to here is 2.4 plus 0.8 plus 0.8, 1.6, 2.4. And then the distance from here to here is equal to 2.4 plus 0.8, which is 3.2. So what I'm going to do next is we're going to take the moment at point D. Okay. So get back to this view. So we are going to carry out static analysis. Okay. Some mention about moment in the z direction at point D. The whole thing will be equal to 0. So the equivalent load of 50 times 10 to the power of 3 Newton per meter is 160 times 10 to the power of 3 at a distance of 2.4. Then we're going to have minus By because it's going clockwise. So 3.2 By. I think it's going to be 0. Over here, we identify our By times 2.4 divided by 3.2 is equal to 120 times 10 to the power of 3 Newton. And it's going up. Okay. Then we do some mention about forces in the y direction is equal to 0. So we are going to have a By minus by 160 plus by sorry that is the dy, sorry. So dy plus by 120 times 10 to the power 3. So we can find our dy. So our dy is 40 times 10 to the power 3 meters. Positive. So the assumed direction is correct. Okay. So next we are going to form our shear force and bending moment equation. So what I tend to do is I will create a table. Okay. So the table will be, we have section. So you have A, then the next one is A to point B, okay. B at point B. Why I stop at point B? Because there's a reaction at point B, okay. Then we have B to C. Then we have point C. And then I think we have C to D. And then we have point D. Okay, so we have a table. I'm going to copy this diagram again. Then the next column will be our distance. Okay, will be our distance. So it will be our x distance. Okay. So in bending moment diagrams and shear force diagram, the geometric datum is always on the left-hand side of the structure, and our x will be moving in this direction. This is because our shear force and bending moment diagram, the x is equal to 0. And the shear force and bending moment diagram is the left-hand side is also equal to what? 0. That's the only reason. So this is 0. Right? So A to B is 0x to 0.8. At B, x is equal to 0.8. Okay. So B to C is 0.8 x, and 0.8 plus 2.4 is 3.2. And then you have 3.2 at point C, and 3.2 x, and we are going to go up to 4 meters. And then is 4 over here. So you write this down here. So why we do this is we know at the end of the day, okay, we are going to have constant for shear force and bending moment at point A. This is a constant. These are all constant because it's not varying as a function of what? X. Okay? All these will get constant. Those that have a range, they're all going to be equations. Okay? That's what we're doing that for. Okay. Then on the next column, is our V as function of X. Okay. And then okay, sometimes it's constant, so I'll just call this our shear force, sorry. And then the next one is our bending moment. Okay. So we know that when X is equal to 0, the shear force is equal to 0, and the bending moment is equal to 0. Okay. So that's easy. So next we're going to go from A, point B, where we have a limit 0x to 0.8. Okay. So now we are going to sketch so as I said, our geometric datum is on the left-hand side. This is X. V as a function of X is in this direction, and moment as a function of X is at that direction. And over here is 50 multiplied by X. The distance from here to here is X over 2. Can you remember why we assume this? Any idea? Can you remember? Those have done 2P. I will not look at Lucas. Lucas have done this at least a year, bit more ago. But the rest of you, any idea why? I think you'll know, but you'll just forget. Okay, this is because we make the assumption of positive shear and positive bending moment. So what do I mean by that? Okay, so what do I mean? So if your analysis is from left to right, like what I've done earlier in the shaft, can you remember that? Right? So if our analysis is from left to right, okay, so our analysis goes from left to right. So left to right is the direction. Geometric datum still fixed on the left-hand side. Geometric datum will not move. Positive shear and positive moment assumption. So this is the assumption that we make. That the shear force is coming down and the bending moment is going anti-clockwise. Okay. So this is the location where we take the moment, the black dot I've done. So that's analysis from left to right. Then if we were to do analysis from right to left, okay, watch this, okay, this is where it's important. Geometric datum did not move. Geometric datum is still the same position, okay. However, now this is your X distance, okay, and this is where your beam is, and the distance from here to here is L minus X, okay, and then your positive shear, positive moment assumption is in the opposite direction. So this analysis is from right. Right? It starts from right, it goes to the left. This starts from the left, go towards the what? The right. So this is what we mean by positive shear, positive bending moment assumption. Very easy. Okay. And maybe you guys were just taught left to right, not right to left. And I'll show you why is it important to know both direction? Okay, because we don't want to be a one pony egg. Okay, we want to be able to do both sides. And I hope I will show later on why, or maybe not. Yeah, I think I will show why this is important. Okay, so now it's very repetitive. Okay, so we are going to do static analysis. Positive is going up. Dimension of forces is equal to 0. So what we have, I do apologize, this is not 50. This is 50 times 10 to the power 3. Okay. Right? Yeah, 50 times 10 to the power 3. Right. Okay. So that is our limit. So we will write this down as minus 50 times 10 to the power 3 x minus v as a function of x is equal to 0. V as a function of x is equal to minus 50 times 10 to the power 3 x. So that is our equation number 1. Okay, so let me see again. Yep, okay. Then we are going to take moment. I mentioned about moment in the z direction at point x is equal to 0. So what this means is we're going to take moment at this pink dot that I'm drawing now. Okay, you see the pink dot over there? That's where we are taking our moment. So this will be, so the 50 times 10 to the power 3x is going to be anti-clockwise. So 50 times 10 to the power 3x, then we multiply by x over 2. Right? Then we plus by m as a function of x.